החומר, לומד אותו מן הסתם, אבל מפיס אותו. לא יודע, לגבי התרגולים אין כל כך מה.
כן, תכבדי אותם אבל
לא היו מלכתחילה.
לא, היו, אבל לא
רגע, אתה אומר שזה...
המקום, קיבלתי מה.
כן.
אני לא ידעתי שיש שם חניה.
תמיד יש.
אני לא ידעתי.
אז אפילו ב10 בבוקר כשאני מגיעה ביום שני, יש.
כן, עברתי מוקדם היום. חליתי לפני 9, אבל לא ידעתי שהמקום קיים. עכשיו גיליתי.
מה זה יש שעות?
ממש קרוב.
מה?
ממש קרוב.
לא,
ממש קרוב.
לא על הכביש
על הכביש?
לא.
הכי קרוב. אין שם?
מה?
מה קורה?
אני?
לא. ממש שילוחו מתחת.
הם צריכים לקרב אותם. צריך...
איזה חום, למה אתה מתחיל?
אני הטריק שלי זה ככה.
כאן בכל אחד.
צריך לגרד אותם. אז הם מוריד את כל השאריות של הטוש ואז הם חלקים אותו.
מה זה כבר...
כן, זה קדים לנו.
קדם.
יש עוד איזה רעיון בבקוץ.
לא הפסקתי להסתכל על זה, לא פתחתי את זה, זה אין לי כוח.
כן, האמת שזה קצת...
כל הזמן דוחה את זה.
כן.
Okay, let's start the class. So today we are going to continue talking about the BCS model, and actually in the second session today, Sarah will do the tutorial on this, so this whole lecture is devoted to finish this topic. So I reminded you what we started talking about 2 weeks ago. We wanted to consider a problem where you have some fermions, let us assume electrons, that have attractive interaction rather than repulsive. And unlike what we've seen for the repulsive interaction, I want to show that the ground state of the free electron system becomes unstable to such interaction. Namely, the system chooses a new ground state that is essentially not a Fock state. It's not a state with a well-defined number of particles, but it gives a lower energy. And therefore, that will be the true ground state. So, and we are going to treat the model in a mean field theory, which is very good approximation in the case where the interaction is weak. And in fact, in many physical examples, not many, but in the most well-known physical example, which is electrons in metals, the approximation of weak interaction is good for that purpose, and it gives the predictions that are consistent with experiments for superconductivity in metals, in that case. For other materials where superconductivity was found with higher temperature, actually this approximation breaks down, and there is no nice microscopic model that is really capturing all the phenomena. Okay? So that's just the side. But this is a very nice success of mean field theory, that in fact won these guys, Odin, Cooper, and Schaefer, a Nobel Prize for the theory. So what is the model? I'm just repeating quickly what we discussed last time. We have here Hamiltonian of electrons is interaction, where the kinetic energy is defined as sum over some energies. Let me put here an index 0 to denote that this is what you get when you just include kinetic energy and no corrections from interactions. And then we have Seeberger sigma, and chi naught, okay, is defined as the kinetic energy relative to the Fermi energy. So when you are exactly at the Fermi level, psi is 0, psi naught. And the epsilon k is, it doesn't really matter what it is. You don't really use this, but if it's really just electrons in a metal or free electron gas, it's just a usual kinetic energy, but its specific dependence on k is not so important for most purposes, because most of the corrections to the Hamiltonian actually come from a very close environment to the Fermi energy. Okay, so we can approximate it by something that is close to E Fermi. Okay, so that's the HK, and then we have the interaction. Here. Interaction is assumed to have the form minus V times factor of half, and sum over K prime to sigma and sigma prime of, this is just the usual interaction term, but when V of Q, the Fourier component, is a constant and it's a negative constant, okay? So the parameter V is defined as positive. Okay, so let me just finish writing. It's CK prime, sigma prime, CK. Okay, so that's the model. And we now do a mean field theory. And in mean field theory, what we do is replacing this term. I'll define it. Okay, minus Q, sigma, sigma, prime plus Q, prime, C, A, prime, sigma, prime, and CK. Okay, so we're doing the mean field approximation, which corresponds to taking separating it into a sum of terms. In each of them, we replace two of the fermion operators by their expectation value by using a contraction. And now, unlike what we did before, we allow more than two possibilities. So before we just had the Hartree and Fock terms, but now we are allowing C dagger, and CC to have a non-vanishing expectation value. So we assume that the ground state is such that they can be non-zero and don't throw them away. So first of all, we take, this is going to be the Hartree. This is yes, the Hartree. This is going to be the Fock. I'm not writing it explicitly, but we are also allowing this contraction, either this or this. Okay, we have always two terms, and let me write down the last term that up till now we neglected. So the first two terms, just a standard Hartree Fock, will not do much, except they will change the kinetic energy. They will replace it by a corrected energy. So with these things, all it does is to replace what I call psi naught by some psi k. Okay? And this psi k includes Hartree-Fock corrections. Okay? And that's why I'm saying we don't even care about the specific k dependence. We just leave it as some function of k, which actually vanishes at the Fermi energy. So psi can take positive and negative values, okay, depending on whether your energy is below or above the Fermi. We get contributions from both negative and positive. And however, we do want to keep the so I'm writing here Hartree-Fock, which is not important, plus, and now we have two terms. We can put an expectation value on either first two operators. Okay, so let me place this by value C A prime, A prime, C A sigma, or I can allow this term to remain as operator, but I replace CC by their expectation. So I put an expectation value this, right? And I should say that let me write here a definition for any operator. What do I mean by expectation value? I'm taking the expectation value now in some new ground state that I'm still searching after, right? I don't know what it is. I'm assuming that it exists, such that for these operators, I don't get zero, okay? And now I have to make an assumption. So specific assumption, because of course this can be non-zero for various under various conditions, but I want to choose a particular constraint on sigma prime, and k prime, such that this is indeed non-zero. And let me write here my assumption that T, K, K sigma, T, K prime sigma. Actually, let me put the prime here, just for convenience of what I do. Next, prime is here, non-prime is here. I'm assuming that this is given by a delta of k and minus k prime, delta of sigma and minus sigma prime times some function of k or some number. This is some number, but it may depend on k. Actually, it doesn't have to be, but it does depend on k in some way. And it is a complex number because we are always allowed to multiply the fermion operator by some phase, right? Because it's not there is always some global phase that can take arbitrary value, and we can always multiply all the fermion operators by the same phase, and that will change the phase of phi. So phi is generally some complex number, okay? And it may, we allow it to depend on k, but the important thing is that this actually vanishes unless k equals minus k prime and sigma equals minus sigma prime. So the only non-vanishing expectation values are when we have a pair of operators with k up and minus k down, okay, where both spin and momentum are reversed. So in a sense, we are assuming that there is some correlation, some Terrin correlation between electrons with opposite momentum and opposite spin, meaning that they are partners of time reversal symmetry. Now, this is a very particular choice. We could make another wild guess that only electrons with the same spin are pairing, but that will have to be consistent with the symmetries of the systems. And in the case where we have time reversal symmetry, there are no magnetic field, no magnetism, no funny stuff of that kind. This looks like a natural choice, and in fact, it's the simplest one we can make. But in any case, it's an assumption. I want to emphasize that here we made a guess, okay? And this is the philosophy of mean field theory sometimes, or the way you apply it. You make a guess on this, and eventually this guess will have to be consistent with the result that you get from the calculation, because it will affect everything, right? Why would it affect everything? Because when we plug in this assumption into the Hamiltonian to get the mean field version, we'll see that it will the resulting Hamiltonian will depend on this form and on the value of phi. Okay? So what let us just go along with this, and therefore, after doing this approximation, we are replacing our exact microscopic Hamiltonian by an approximate one, a mean field, which I denote as HBCS, okay? So it's reduced to an approximate form, which can be written like this. So it's, first of all, we have the kinetic term, which I'm rewriting. Okay, with the psi, the corrected psi, minus, now we have two terms, delta, sum over k, or actually, let me just put the sum of k. Better. So here we have two terms. Delta times and I'm notice that here I'm using just one index k. I will define it in a minute. Plus the Hermitian conjugate, which is okay. This is what you get. Let me just show that. Yeah, this is the form I like. Where here I make a definition here. Let us define K to be, okay, let me first write down delta. This is a definition of delta. It is the interaction parameter V times the sum over K of phi K, this phi, where K is a shortcut notation for K vector and spin up, and minus K under this definition will be its time reversal partner, which is minus K vector and spin down. Okay, and phi K, and let me write explicitly what is phi K, which of course satisfies these constraints. So this is phi K here is the expectation value of C minus K under the same definition, okay, which is finite number. That's what we assume. Okay?
Is it the same phi in
the same phi? It's the same phi. It's just that here it's the same phi.
How about the vector sign?
What?
The
So K.
vector.
Yeah, right. Okay. So this phi of K, we assume it not to depend on spin anyway. Okay, so it just depends on the K vector. Right? Okay, so actually, Sal will go through some subtle details in the derivation, but with how we count the spins and all that. But and I forgot to mention something important, that this is an approximation of the original Hamiltonian up to an overall constant. So there is some constant correction to it, which is not an operator, so we don't need to worry about it. But this constant is actually important for computing eventually the total energy, because if, for example, we want to compute the ground state energy and compare it to the energy of a free electron gas, we want to convince ourselves that it's going to be smaller. So this constant may be important, but at the moment I'm ignoring it because it's not, it's just a constant. Okay. Good. So now what is the problem? So this Hamiltonian is very simple, is simpler than the original one. I mean, in fact, we can exactly solve it because it's once again quadratic. Okay, we already saw that whenever we have just one body operators and all the terms have only two particle operators, then we can, maybe we have to diagonalize it, but we can deal with it in a simple way, okay? But it is different from what we've seen up till now in the course, because usually the one-body terms that we saw, even if we wrote it in a basis where it's not diagonal, were C, C dagger. And here we have terms that do not concern number of particles. They're either C, C, or C dagger, C dagger. Okay? And therefore, we already see that if we want to represent it in some diagonal form, to find the new set of quantum numbers or the quasi-particles that describe it, they are not going to be electrons. Okay? They are going to be something that should somehow mix electrons and holes, right? Because this cannot be diagonalized by a state which has a well-defined number of particles. Okay? So let me bring it to a more compact form that in which it will be transparent how we need to approach the problem. Okay, so what we do first, before I do it, there is some trivial step that I want to do, which in order to bring the two terms here on the same footing. But notice that the first term, I wrote it as a summation over k vector and sigma. And there's only one such term, but the two spin states are represented for each k vector. Okay? I can rewrite it in a way that will turn out useful. Let me erase it. This. Yeah, so let's just look at the term, the kinetic term. Yeah, I can erase this. Let me do the following. I'm always allowed to separate it to two terms, one with spin up and one with spin down. Okay? You agree? So I'm writing it like this. Okay, up. No, sorry, then I don't need to put it in the down. Psi k. C dagger k up, C k up, plus other sum. It looks stupid what I'm doing, but you'll see in a minute why. Of course, psi is the same psi. K down. Okay. Right? And here I'm only summing over k. Now, the second term, you see that here I can rewrite the sum as sum over k. Okay? According to my definition of k without the vector sign, the first term is actually a sum over k, and the second term will be a sum over minus k if I replace k vector by its minus. But it's always a dummy index. Remember that we are summing over k vectors from minus infinity to plus infinity in any direction. So you can call the variable k or minus k vector, and it's the same thing. So I can replace the indices. Allow me to do it on the same equation without writing from scratch. This. K, and this is going to be just k and k, and this is going to be minus k, okay, where I'm using the fact that psi does not depend on the sign of k, okay? And it's a symmetric function of k vector. Okay, and that is why do we believe that it is? Oh,
we break time reversal.
Exactly. If the system doesn't break time reversal symmetry, the sign of k, whatever it is, including the Hartree-Fock correction, is equal to minus k, and therefore it's just the same parameter. Okay, so now why am I bothering you with this? Because now I want to do another replacement, which is I want to replace the C dagger C. I can always use the anti-commutators of the fermions to rewrite it as 1 minus C minus K, C minus K dagger. I want to switch between the C and the C dagger. And because this is the same index, the anti-commutator satisfies the delta, right? Because I remind you the anti-commutators for fermions is that C, okay. This is, sorry, with the dagger is a delta K prime and delta C minus. Right? Okay, so I can write it like this, and the one will just give me some correction to the constant, right? Will give me a correction which is a sum over k of psi of k. Okay? So up to a constant, what I'm ultimately getting is, and let me rewrite it here. I'm getting that DCS Hamiltonian H S equals, so the kinetic term can be expressed as a sum of two terms, sum over k of psi k, ck dagger, ck, minus psi k of c minus k, c minus k dagger, okay? And then the constant will now be a different constant, but it's still a constant that I'm not writing. Okay, so that's my result. Okay, that's my Hamiltonian now. Okay. It has 4 terms, if you like, and it's written in a bit of a funny way, but all these terms are some combinations of C and C dagger. Okay? I can write, let's forget about the constant with your permission. I can rewrite this long line in a compact way. If I now make a definition, we no longer need. Let's now define some creature that is called a Nambu spinor, after a Japanese physicist Nambu, and it's the following. I'm defining an operator which I call psi-k b, and it's an annihilation operator, but it's actually a two-component vector. It has the form of a spinor, okay, with two components. The top component is the annihilation operator ck, and the lower component is C dagger. Okay?
Dagger of
Minus K.
What?
C dagger of minus K?
Oh, C dagger of minus K, yes. Where I emphasize that this K is defined in this form, that K is the K vector up, and minus K is minus K down, the time reversed partner. Okay? So this is a funny spinor which has two components. One is annihilation, and one is a creation operator. Okay? Great. Now I'm claiming that I can take this line, okay, this operator part of the BCS Hamiltonian, and rewrite it in the following form. Sum over K, psi dagger K, HK, okay, I'll define everything in a minute. Now, first of all, before I write what is HK, is going now to be a matrix, two by two matrix. What is psi dagger? Psi dagger is just the Hermitian conjugate of this, of psi, right? So let me write what it is, just for good measure. If psi k is, first of all, it's how do you call it, a column vector of ck and c dagger minus k, then psi is going to be a row vector where the first component is ck dagger, sorry, this is a dagger, and the second component is c minus k. Right? Okay, so I think you can easily convince yourself that if I'm writing now, I'm erasing this, but you already know what it is. If I define HK to be, write it down here, HK here is defined to be 2 by 2 matrix that has here psi k delta star and minus psi. Okay, and if you just plug it in and do the algebra, you can easily convince yourself that you get exactly the form that I erased now. Okay? Okay, so that's a very nice...
So this is like exactly the same HK.
What? Sorry?
It comes out to be the same HK.
Yeah, that's the, so this no so before I wrote a very long line for HBCS and claiming if you plug in this psi, this HK, this psi K dagger, and you just do the algebra, multiply a matrix by a vector and blah blah blah, you'll get exactly this. And of course up to a constant. Okay? There's also the constant. Okay, so it's just the operator part. Yes. All right? Just do it for yourself, and maybe you'll have it in your homework, but even if you don't, I recommend to do this really simple calculation, because you may need to do it in your exam. Or something like it. Okay? Good. So, great. So it's very compact, but still it is now it's not. It doesn't have a diagonal form, and we want to replace this. We want to basically diagonalize it. Namely, we want to replace it by a form. This is what our goal is, to find some transformation that diagonalize it, so it will acquire the form sum over k of ek, okay, where we already see that C and C dagger, we knew it from the beginning. C and C dagger are not eigen operators of this Hamiltonian, because the Hamiltonian mixes C's and C daggers, as a result of which you have a non-diagonal 2x2 thing, and we want to find new operators, I call them gamma k, such that in terms of them, and some constant, of course, overall constant, up to an overall constant, this will be the Hamiltonian. And Ek is the eigenenergies, namely these are the eigenvalues of this 2x2 matrix. Okay. By the way, there's something nice that we already see. This Hamiltonian is already diagonal in K, right? So it's already diagonal in K. So each K is a separate sector. And that's a simplification, because you know, if we made some more complicated assumption about delta could be a function of two different K's, and then we couldn't write it in this way. But we see that we made, under this very simple assumption, that delta is just a constant, it's a one parameter. Okay? We get something that is separable into independent cases. Okay? So it's diagonal, it maintains the momentum and spin as good quantum numbers, but it mixes, what does it mix essentially? Creation and annihilation operators. Okay? Okay, so the way to treat it is just to diagonalize a 2x2 matrix. Okay? Okay, so we in fact define a transformation, a unitary transformation that takes us from the psi to some new number vector. So let me define here gamma. This is just name gamma k, capital gamma, to be a gamma k, gamma minus k again. And I define a unitary transformation. Gamma is given by some unitary transformation which depends on the index k of psi, such that hk, if I multiply by uk minus 1 hk, okay, we'll have a diagonal form, okay? And the diagonal form that we're going to get from this, let me first call it, let me just give it a name, but we are going to see that this is just plus or minus the same thing. Okay. And these are the eigenvalues. Okay. The eigenvalues of this 2 by 2 matrix. So to find the eigenvalues is easy. It's easier than to find the transformation. Okay. And let us find first of all the eigenvalues, because we want to know what are the energies of these excitations. Now I want to stress something important. So what are going to be these gammas? Let me write down explicitly what this means, because this is in a matrix form, right? This is a vector, which is a 2 by 2 matrix times vector. And I'm defining, I think we erase something, which I erase. Okay, so UK unitary matrix, and for simplicity, let me assume that a unitary matrix can have complex components, but for simplicity, let us assume that they're real. Okay, so there are two parameters, u and v. I can associate them with some angle, call it theta. Such that, why does it have this form? This is a unitary matrix, it's a rotation matrix, right, in an angle theta. And why is it important that it's unitary? Because you can easily show that if we want to replace fermions by fermions, right? The psi is a combination or is a spinor of C and C dagger, which satisfy anti-commutators. I want the gamma k dagger to satisfy the same, okay? And then we can say that they're new fermions. So for that to hold, in order for gamma, I want gamma k prime dagger to be a delta of k and k prime. That will work provided that u is unitary, or in other words, that u squared plus v squared is 1, which is by definition if they are cosine. Okay? Now, what is it? If I'm just opening this matrix notation, I find that gamma k is going to be given by little u, uk times v minus v of c dagger minus k, and gamma dagger minus k is dk dagger plus uk of, and that's what it is. Okay, and by the way, this is something I don't want to get into this. Maybe Sarah will discuss it in the tutorial. But in order for this to be consistent, you need to obey that if I change k to minus k and put the dagger here, I should come back to second equation. That will work provided that u and v have some symmetry properties when you change k to minus k. Okay? You can almost easily see what they are, but let's not get into it. It's technical detail. But what I just want to stress that it's a linear transformation. This is called the Bogolyubov transformation. Okay, actually, this is what it is, and here it's written in an explicit form. And we already saw a Bogolyubov transformation earlier in the course, a few lectures ago. You remember? That was when I wanted to introduce some new annihilation creation operators such that the full Fermi sphere will be the vacuum. But the Bogolyubov transformation we had then was a very trivial linear combination of creation and annihilation, such that the coefficients are either 0 or 1. Here, they can be anything. In principle, for every k, you have some different parameters which are parameterized by a rotation angle theta. Okay? Yes?
You can always add some phase to the
Let's discuss it later. You are right. Very important. We come back to it. First, we are doing the same thing. Yes, it's a very important thing. Okay, so this is just for simplicity that I chose them to be with. But what are the resulting eigen operators or the new quasi-particles are linear combinations of creation operator and annihilation. Not just any annihilation and creation, because it's a superposition of annihilation of state k and creation of its time reversal partner. And this is what they are. And u and v can be anything between 1 and 0, and in particular, you can have a specific k in which they are equal. They are both equal, and they have to sum up to 1, so there can be 1 over square root 2, and then you will get a superposition of an electron and a hole. Okay? A coherent superposition. So these are the quasi-particles, and that already makes us feel comfortable, because as we said in the beginning, the Hamiltonian, he has a form that doesn't preserve number of particles. So its natural, its eigenstates are not either holes or electrons, they must be some non-trivial superposition. And one can express, so that is something that Sarah will do in the tutorial. You will find explicit expressions for u and v, and they will be, of course, dependent on psi and delta. Okay? Okay, so I'm not writing them down, but I want to find the eigenenergies, because that's the easiest thing when you have a 2 by 2 matrix, to find the eigenvalues is very easy. Okay? You don't even need to write the unitary transformation. Why is it easy? Because you look for a determinant of the Hamiltonian minus lambda I. So, okay, so let's do that. So maybe there's actually something that I want to write on the side. Very useful formula. I don't know if you've seen it, but very useful. When I have a general matrix, and let's 2 by 2 matrix that is Hermitian. Okay, of course you can generalize to non-Hermitian, but we are only interested in Hermitian matrices. So the eigenvalues lambda 1, 2 are going to be first the average of A and B plus or minus, these are the two solutions, square root of A minus B over 2 squared plus B squared. Okay? This is already the solution of H minus lambda already, that's a solution. Okay? Okay, now let's, this is a general formula. Let's apply it for our Hamiltonian, which has a very nice form because the first term is going to be 0. Right? So what are let me call it EK plus minus, the two solutions are just plus minus the expression that you have in the inside here is going to be just psi k square plus delta square. And in fact, this plus minus is kind of a redundant representation because if we think of it in the diagonal form, the Hamiltonian will have the form, let me now rewrite it. So, yeah, I think here I can erase it. So I said HBCS is now going to be, there will be some constant, which I call epsilon naught. This is actually the ground state energy, plus the sum over K of EK gamma K, and in fact I claim that this already takes into account in the diagonal form, the matrix form I'll have here EK minus EK, but the vectors are nothing but gamma K and gamma dagger of minus. So it's actually the same term if I do the same trick I did before, which is to replace this by 1 minus gamma dagger and put a minus sign on all the k's, I get the second half. So it's just a double counting. Actually, if you do it carefully with the spins, I can actually write it a little more carefully. it's going back to the spin and k vector notation. And then it has two spins. One I can write is plus ek, and the other is minus ek. And what is ek? So my definition of ek here is the positive square root. Okay, so here ek is just this positive energy. Okay. Okay, what can I say about the spectrum of the new excitations? Yeah?
How can you assume that it should be the positive one and the negative one?
No, it's what I'm saying is that if you look at what this is, this is just a matrix in the diagonal form. This is just a matrix that multiplies gamma
so
k. It's just the same. It's a kind of a redundant representation of what we had. It's similar to what we had before for the kinetic energy. Okay, you see? Actually, this was actually a redundant representation. If you like, we're separating the spin up and spin down sectors, and we do the same here. Okay? Great. So what are the how should I think? Yeah.
When you are doing them, you're assuming that gamma has an algebra of fermions, but doesn't it depend on the value
as I said,
of
it follows from the unitary transform. So if you I already erased it, but if psi is number spinor of C dagger, and it obeys anti-commutator because the transformation is unitary. Actually, if you like, if I explicitly compute the anti-commutators, I can see that in order to get the delta, this requires that the transformation will be unitary. And that is also true if I choose there is some phase here. Okay? So in order for this is dependent on, this requires that u plus b will be 1. Okay? That's why it's a unitary transformation. So these are new fermions. These new fermions are some superposition of electrons and holes, and they are. And notice what is the meaning of gamma. Gamma is an annihilation operator compared to the new vacuum. Okay, so we actually defined here a new vacuum, a new ground state, our what we call the BCS. Okay, so we define here a new ground state in which we compute all these expectation values such that for any k, gamma k acting on it has to give 0. Okay, and in fact, this definition, if you like, of the ground state allows us to find it because we still don't know what it is. But we know what is gamma. We know to write gamma as a combination of C and C dagger, and then we have to define a state such that acting on it with any gamma gives us 0. Okay? But before that, I want to say something about the spectrum. So what is the spectrum of these new excitations? There is a ground state. This is the vacuum, if you like, ground state. But it's really the ground state energy, above which you have excitations, because I defined Ek as positive energy. And right, so Ek, if I plot it as a function of K, what is it going to be? How does it look like? Remember that psi, we don't really care what it is, but we know that psi, okay, I already erased it, but first of all, it's a symmetric function. It doesn't depend on the sign of K, but we also know that it's defined as some kinetic energy or some energy minus E Fermi. So what is its value at E Fermi or at K equals K Fermi on the Fermi surface of the original?
The gap, the difference.
What?
Delta inside the...
That's right. So psi is actually 0 when K equals K Fermi. Okay, so if, let me here choose some direction in space, doesn't matter. And this is K Fermi, this is the Fermi surface. Okay, at the Fermi surface, psi is 0. So what is Ek? Ek is delta. Okay, so that's okay. There is a gap, an energy gap, given by the absolute value of delta. The delta, by the way, is, we already saw, it's a complex number, right? Because it's defined as a sum of a complex numbers. It's generally complex. Coming back to your question, we'll get to it. But, and therefore, that's why in the Hamiltonian we have delta and delta star, but the energy only depends on its absolute value. Okay? So it's positive, and then this is how the spectrum, the dispersion looks like. Very close to the Fermi surface, it's almost constant, and then it disperses. It's more or less like a hyperbola, because close to the Fermi energy, we can always linearize psi to be something linear with K, and this is how it looks. Okay. So what is the lesson? First of all, we found that there is the natural eigenstates of this field, this BCS Hamiltonian, are Bogoliubov quasi-particles, which are combinations of holes and electrons, and they have some ground state energy, which if you compute it, you find that it's negative, so it lowers the energy of the free Fermi gas. And of course, all of that is provided that delta is finite, right? And then there is this ground state is separate from the excitation spectrum by a gap, okay? Which means that if, for example, you are at low temperatures, at 0 temperature, you're going to be the ground state. At finite temperature, you can always have some quasi-particle excitations, but they will be exponentially small. Okay? As long as your temperature is below some critical temperature, which is related to this gap. That's what it says.
The gap will be 0. That's the critical.
At the critical. So actually, okay. For a given finite delta, there is a gap in the spectrum. But if you actually, let me answer that. Go back to the finite temperature. So just focusing on the 0 temperature ground state is there is some ground state energy. Believe me, it's negative, and you'll do actually a calculation in your homework finding it, and it's separate from the excitation spectrum by a gap. So, of course, this doesn't tell you why, this doesn't explain why the new ground state is superconducting. That takes more things to explain, but it is a new ground state. And I actually can find a form. We want to be able to write it in terms of the second quantization, in terms of the creation and annihilation operators of the original electrons. So to do that, I use the fact that what do we require of the ground state? And it's just its definition, if you like, that any gamma k will annihilate it. Okay? So, your permission, I'm erasing it. So, and let me write gamma, the operator gamma is that's what it is. That's what the transformation tells us. And what we require is that for any k, this acting with gamma on the new ground state should give me 0. Okay, that's the requirement. Okay, so let me write down a solution, and to prove that it's indeed working, just substitute and do the algebra. Okay? And I think you also have that in your homework, the ones that is related to this. So this is what BCS find. And it's not a unique way of writing it, okay? But it's one that is most convenient, most transparent. It's a product of overall k, where again, k is a combination of k vector and spin. And for each k, you have a uk plus pk c dagger of, let me just do it order, k c dagger minus. All that acting on the vacuum, right? The real vacuum. Remember that just a free Fermi C is a product of all the CK daggers acting on. That's a Fock state. That's the free Fermi state. And well, actually, it's k smaller than 2f. That's the free Fermi surface. It has well-defined number of particles. Here, by the way, I don't have any restriction on k. The information whether now depending on where is your what is your k, bigger or smaller than kf, one of these coefficients will be 0. Okay? So, for example, if you go to k vectors that are much above the Fermi momentum, you are going to get that v goes to 0 and the uk goes to 1, and then that's why you get something empty. Right? The vacuum, yeah. Okay. So this actually interpret what is the, why is this? As I said, this is not unique, but it's a very nice way of writing it because it's very intuitive in a sense. Okay, what does it describe? For each K, we are occupying and this is a coherent superposition. Okay, so U and V are between 1 and 0, and if one is close to 1, the other is close to 0. They sum up their absolute value square, sum up to 1, right? And so it's a superposition of nothing and a pair. Okay, so instead of having just occupying all the electrons with K and the electrons with minus K, it's either a pair of electrons and or a 0. Okay? That's the preference in terms of the original electrons. And this pair, this is called a Cooper pair. After Charles Cooper, was one of the founders of the C of the BCS. So what is this pair? It's a pair of electrons with opposite momentum and opposite spin, tangential partner. And inside the ground state, you have many such pairs, right? I mean, you have with some weight, which depends on the VK, you have the electrons are paired, okay? And actually, if you look at, I'm not writing down the expressions for UK and VK because Sa will do it, but let me plot them as a function of K, where here I put KF, okay? So let me use different colors. So V looks something like this. This is kind of a Lorentzian function. This is V of K, and maybe I should cut exactly at KF. Exactly at KF. Okay, actually, what I'm plotting is sorry, it's not U and V, it's the absolute value. Be more exact, and this is 1, and this is U. Okay, something like that. So close to the Fermi energy or Fermi momentum, both of them are not 0 and 1, and in fact, at the Fermi sphere exactly, at the Fermi sphere exactly, they are going to be square root of 2, so that they sum up to 1. The absolute value square sum up to 1. Okay? So this is when you have a completely coherent superposition of an electron and hole with the same weight. And if I'm plotting the product of U and V, and here I have this Fermi. Now what I'm plotting now is the product U and K. Okay. How does it look like? Actually, you can qualitatively guess it from here, because you see if V goes down, U goes up, the product is almost 0 except near the Fermi momentum. So in fact, it is looking like this, okay, where the width of the function is of order delta. Okay? And in fact, you can write down an expression. So I leave this because it. You can explicitly calculate this because, as I said, U and V are just parameters of unitary transformation that diagonalizes the Hamiltonian. You can compute it as a function, and it's becoming a function of psi k and delta. And the product, uk times vk, which is, if you like, it's a cosine times sine, or it's a 1/2 of sine of 2k theta, if I use trigonometric formula. It's going to be where k, to remind you, is square root of psi plus. Okay, yeah. That's the result. By the way, this relation is also true if U and V are not real. For example, let's, without loss of generality, let's assume that U is real, but V has some phase. Okay? We always have the freedom to do that because it's up to multiplication by a global phase. Then this phase will be carried out to delta, or the other way around. So if you assume that delta is a complex number with some phase, that same phase will be carried away to V or U. You choose either of them to be the complex. Okay? Right? I mean, you can choose delta. Let's say if you choose delta to be some positive number, gives you real U and V. Now I change, sorry, if I change delta to delta, which is positive, I change it to a delta times e to the I phi. This phase, and phi is some arbitrary phase. This arbitrary phase will have to appear in V in order to satisfy the algebra. Okay? All right. So, but why am I interested in this product of U and V? Because notice that this one is non-zero only in close proximity to the Fermi energy, right? Actually, from here you see why it has this shape. It's like a Lorentzian, or not exactly Lorentzian, but the same shape, right? Because the denominator falls when psi goes away from zero. And when it's non-zero, this is called the coherence factor. What does it signify? When it's non-zero, it means that you really have a quantum superposition. It's really, it's like entangled state, okay, of an electron and hole. So this is the case when U times V is maximal, then you really have the operator, the eigenstate that you create is an even superposition of an electron and hole. So it's something that the number of particles is not well defined. Okay? So Now, coming back to, I want to emphasize now, let us go through the philosophy. What was the philosophy? We did a mean field approximation where the starting point is to say, aha, let's pick a new ground state in which this phi is non-zero. Okay? And we just guessed it. But this phi is actually something very specific. It's the expectation value of an operator in a ground state that now we have this form. Okay? And by the way, I think I forgot to mention, but if you take this operator from the definition and apply it on the BCS state and just do the usual algebra with using the anti-commutator of fermions, you can see that it gives zero. Okay? This is a very simple exercise. I don't do it explicitly, but it works. So this is the ground state, and now I can actually, so what we did was we assumed that this is non-zero. We used it to define delta. With the delta, we got a Hamiltonian, which was this 2x2 matrix. We diagonalized it, we found eigenstates, we found the energy spectrum. Everything is beautiful, except you have to keep in mind that it all hinges on this thing being non-zero. And not more than that. It's not only that. We also require that if we directly compute it, now that we know the ground state, we can compute it, right? And we should equate it to delta, and it should give the same delta that is somewhere buried here, right? Because the ground state, the expectation value of the pair operator depends on delta itself. So in order for all this theory to be correct, we need to satisfy a self-consistent condition, and this is called a gap equation. It's a self-consistent equation, which tells me the following. Let's compute this, plug it into here, and equate it to delta and see if we have a solution. So let me write down what you get. So first of all, this is something I'm not doing the algebra, but again, it's a simple calculation, and sorry, let me put here K and minus K, which is what I call the phi. Okay, you can explicitly compute it in terms of the gammas. And how do you do the calculation? You invert the transformation to write C in terms of the gamma and gamma dagger. You get 4 terms, some of them vanish, and you get in the algebra just exactly the coherence factor. Okay. That's what comes out. And now I'm writing the self-consistent equation. I'm taking this, let me rewrite it. And it's called the gap equation. Delta has to be equal to V times the sum over K of phi K. But what is phi K? It's UK VK. And UK VK is this. Okay? Let me plug it in. So I get delta equals V times the sum over K delta over, we write EK now explicitly, psi K square plus delta absolute value square. Right?
All your
Okay.
calculation at 0 temperature?
This is all at 0 temperature. Exactly right. Actually, you're completely right. If I do it at finite temperature,
It should get
the numerator, and yeah, and this is true for t equals 0 if the temperature is non-zero, the U times V is multiplied by a factor of 1 minus twice the Fermi energy. And of course, it will reduce the right-hand side in such a way that there will be a critical temperature where there's no longer a solution. But let's first see what happens at 0 temperature, because this is already an important, a simple but important message. This is our self-consistent equation. Forget about the middle. Here we have an explicit relation. We have to equate delta to what? To constant times the same delta, right? And then multiplied by some function of k that we have to sum or convert to integral. It doesn't matter now how we do the explicit calculation. But what are the possible solutions of this? First of all, there is always delta equals a trivial solution, right? Because delta appears as a multiplicative factor on both sides. So one boring possibility is that it will be 0, okay? And then, of course, it's satisfied trivially. But if it is non-zero, then we are allowed to cancel it, right? So let's assume that it's non-zero, and then we cancel it on both sides. And then what we get is that the left-hand side, what will remain now is just 1. So 1 equals V times the sum over K of 1 over a square root of. Okay. That's the gap equation. And notice that in what sense this is an equation. It's an equation for what? For delta. Okay. But delta does not appear directly. We have to do some calculation to get an explicit expression for delta. It can be done, but the first question is whether it has a solution that is non-zero. What is the condition for getting a solution that is non-zero? We have something times V has to be equal 1. In fact, I can already see that there is one very clear condition in which it will not have a solution. If V was negative, there would be no solution, because this sum is a sum of a positive function, and it has to be positive. So only provided if V is positive, then it can work. And this, coming back to our origin, V was the parameter that introduces an attractive interaction. So a passive interaction will not give you such a states, but the attractive interaction will always give you a solution. Okay? Will always give you a solution. And now you can work out how this solution is. In order to find the delta explicitly, you need to solve the sum over k, right? Equate it to 1 and invert the formula. You can do it a bit over time, so let me just, let me not do it, but you can make some approximation, like converting it to an integral, replacing the density of states by a constant. So something that is working for a metal will give you an exponential expression for delta. This is not an important detail. I will post my notes on it. But so you can find the result. It's giving something that can give you a few Kelvin. If you convert it to critical temperature, it will give you a few Kelvin, which is consistent with superconductivity in metals. Okay, or typical numbers. You cannot get from it room temperature. Critical. It's really an exponentially small. There's an exponentially small dependence on the interaction strength. Okay, but the other thing I wanted to mention, and then we'll make right, is distinguish the phase of the complex that I mentioned. That could be the solution. Depends, the solution of this non-trivial delta is that delta can be a complex parameter. The energy and the gap equation and all that does not depend on the phase. You see, it does not. It depends only on its absolute value.
The Hamiltonian will be dependent.
The Hamiltonian will definitely be dependent.
So it's break.
Right, exactly. That's exactly true. So that's exactly right. So I can solve it for, let's say, delta being the positive constant, and I get a solution and the delta absolute value has the physical significance of an energy gap. Okay, so it's a real number, but delta itself is actually a complex number, and I can always assume it to have an arbitrary phase. This phase will carry itself to the coefficients of the unitary transformation, such that there is still a unitary transformation, and anything that is related to energy spectrum and all that will be the same, because it will not come in. So in fact, what I'm telling you is something very remarkable. Once we satisfy the gap equation, we no longer have a solution. We have an infinitely many solution, because this arbitrary phase can be anything. Okay? And indeed, exactly as you say, we get a Hamiltonian, and in which there is a parameter that spontaneously breaks a symmetry that we know exists for any quantum system, and that's gauge symmetry. Okay? Because we can always, it's really coming from the fact that this phase is related to the phase we can always add to any quantum state. Okay? So this is an example. Once we have this new ground state is an example of what we call in general spontaneous symmetry breaking. It's exactly like ferromagnetism, if you like. In a ferromagnet, you start from a system that is time reversal invariant, no external magnetic field, and it spontaneously creates magnetization in a particular direction. How does it choose it? In practice, it may be due to some external field that we apply just for fluctuation, but it spontaneously breaks the symmetry. And this is exactly the same. Okay? So just the last comment is that if, because the electrons are charged, if the state is coupling to electromagnetic field, this will actually, this gauge transformation is actually not exist. This phase actually couples to the vector potential. I'm not showing it, we just mentioned. And that coupling is what introduces the Meissner effect, which you heard. You know, this is what makes superconductors float and magnets. And the story comes from that. Okay? But it's really an example for once we have a transition into a superconducting state, and it's an example of a phase transition, just like magnetism. Then this is a broken symmetry, and the symmetry that is broken is a gauge symmetry. Okay, so that's it, and so as I said, Sar is going to do some, complete the holes here. But next week, we start a new topic, the last topic of the course, which is the path integrals. Okay?
What?
Path integrals.
Are you ready for the problem? Yes.
שאלה יותר כללית, איך, נגיד כאילו שאני כותב איזושהי נתוניין אחר, איך דלתה יכולה להיות תלויה בקי? אולי פאי יכול להיות בקי? אם אני סוכן על הקי...
אז אם יש לך, אם תחת ההנחה הזאת זה לא יהיה. שזה מה שנקרא S. אבל אתה יכול לחשוב על... יש לך מילטוניאן שקורי יותר מסובך, אז יכול להיות שיהיה לך למשל זוגות שיש פה איזה זוגות טריוויאלית. זאת אומרת, הזיווג הוא לא של K ומינוס K, אלא K פלוס Q או משהו כזה. יכול להיות משהו כזה. ואז לדלתה יהיה פרוט ו-K, וזה יהיה יותר מסובך, אבל העיקרון אותו. טוב? שרתי לך מה לעשות. מה? אני חשבתי אפילו להציע לך שנתחלק כבר, אבל זה לא טוב, כי שבוע אני מתחילה נושא חדש, אז פדגוגית זה לא אידיאלי. כיף נגמור היום.
זה בסדר.
יאללה, להתראות, ביי.
אז זה לי ככה. נראה, אתה לא מבין לעבור. לא כזה בא לעבוד, אני עובד לרוב מהבית, אבל... אין חייבת לבוא. קורסים, מומלץ לבוא. אם אני אעבור הבנה שם. אבל לי בנושא. לא, אני אומר טוב. זה נורמלי. מה? למה האופי שלי? איך כמה נורמלי לא טוב חיפה. אולי. מה שטוב בזה שם. כן. בסדר. אוקיי, בסדר. אבל נגיד 20 דקות נסיעה זה... יותר מדי ממהר. אני כן רוצה... זה השיקול.
אפרת אף פעם לא כתבה לנו את הראשי תיבות. אני חושב שטוב שהיא לא כתבה.
אבל זה לא היה ככה.
אתה רואה להם ברדי קופר שייפר?
כן.
תיאורי?
כן.
אתה יכול להכניס גם שם תיאורי.
כן, לא, תיאורי בסדר, היא כתבה. את הראשי תיבות של BCS היא לא כתבה. טוב שהיא כתבה.
מה הוא נכון הראשון? לא, זה ברדי.
אני מאמין לך.
למרות שזה הציטוט של...
זה יום רק להשלים, יש 12 בלילה עד ל-4 יש פה שיעור עכשיו של...
אני מתקדם.
כל הזכויות שלו, אני מסתכל.
הבנתי ששאנחנו עברנו לפי... ההנדסה יש להם רגיל. רגיל, ההנדסה היא טוב סתם. לא, אני יודע, יש שם יפה. ההנדסה בלי מזכר. גם פה נקרא, זה יפה פה.
אני אוהבת אותה.
בתרומה הזאת שלו. אבל עדיין הרבה. לדעתי הם השקיעו בחברי סגל. לדעתי לא גם.
כל כמו שאתה משקיע, בפנה הכי כסף. הספר אחד ולא היה לה תלוי, היה לה תלוי, יש לנו רק בצלח גדולה. אבל בכלל
אני אוכל ג'ירף כבר איזה שבוע. כן, אני לא יכול, אני חושב שזה היה קצת גיהנום.
כן, אבל זה ישתלם.
כן, לא, יש כאלה 78. נכון, לא, אתה צודק, אני מדפיס. לא שאני עושה, לא שאני מדפיס, לא שאני בוא, אני לא יודע. זה תוכל להדפיס. אתה רוצה גם להדפיס את זה, זה גם יכול לעשות 200 שקל. זה כאילו אומר שהם העבודות חברות שלך, נכון? העבודות שלך.
כן. זה נהיה בינוי ככה, נהיינו
אז גם יש להם מעבדות כאלה. תראי אצלנו שאני תפסתי את בו זה רק אני שהגיע כאילו, גם זה קשים הוא פה, נכון לא יודע, לא, אבל התיאוריה שלהם היא לא תיאוריה כן, שדות ראיתי אותה בכנס כן נכון זה היה בוקי שלך שמונה התחלנו סוף בסדר שגם בהנדסה, אבל הוא לא יודע כלום. זה בסדר. בחדר, כאילו. באתי במעבדה, ואנחנו לא תוך חדר. אבל הם עוברים. כאילו, המחלקה עוברים.
בסוף הלכת לחיפה לזה?
במושבה הגרמנית, הייתי ביפה, הייתי לשוק הפשפשים, שגם יש אווירה וזה יותר קרוב כאילו, אבל זה פחות. סתם, לא היה לי זמן. כאילו, יש לי את החופש של להשלים תארים, שיעורי בית וזה.
ושמת?
אתה יודע שחוץ מהשיעורי בית של ירדן אחרי?
כן, עשיתי הכל חשוב. זה הכל נפלאתי.
תשמע, אנחנו באיזושהי שהוא אמר לי שהוא רוצה גם שורש להתכנס במשוואות אותי.
כן, האמת שאני גם, עד שהוא אמר לי לא יודעתי.
כן, הוא לא כתב את זה, אמרתי, הוא לא נגיד בקבוצה כי אנשים בוודאות לא יודעים.
הוא לא כתב את זה, הוא ישלח מייל.
זהו,
הוא לא כתב את זה.
נראה לי שהוא שולח, אני לא עושה את זה, כדי ש...
לא, הוא ישלח.
הוא ישלח, עד שהוא ישלח אני לא...
הוא צריך לשלוח אתמול וזה כנראה זה בעיה, כי זה לא שלח.
לא, אני בטוח שהוא ישלח, אבל עד שהוא מוסיף, הוא מנצל את זה מנטלית כדי להכחיש לחלוטין את זה שאני צריך לחזור.
לא, אני דיברתי איתו, רק על זה אמרנו, כי לא...
אני גם לא, בהתחלה אמרתי מה, אני אולי פספסתי שוב, אני לא חושב שזה, זה לא כתוב בכלל.
לא, זה לא כתוב בכלל.
אז כאילו בסדר, ברור שאני ככה מתבדר, זה הרבה יותר קל.
הוא גם אמר לי שהבאת כמה תחדרים שהוא ביקש.
נכון, זה גם אמר לי, שעובד לשלושה. שזה הגיוני, כי זה באמת סתם מיותר.
זה ארוכה ממש.
כן, ולעשות בינום, כל מיני כאלה, ויש לך אחרי זה בינום של 3 דברים.
כן, כן, זה לא נכון.
אז אתה גם, טוב, זה כזה, הקטנת תורה שלו, כאילו הוא יכול, הוא גם ביקש על אפסילון בריבוע, כאילו מה שבא קודם. אז נגיד את השור המתבדר, אז אתה יכול לשאול אפסילון בריבוע של מי? של ה-Y, אחרי הסקיילינג, או של ה-X? כי נגיד הסקיילינג שלך היה 1 חלקי אפסילון, אתה מגדיר Y.
כן, כבר מתבדר, שאתה תחלקי דלתה?
נגיד, כן. אז זה גם מה שאני חשבתי?
לא,
אבל אתה יכול להגיד, אוקיי, אבל אולי מתכוון ב-X ואתה צריך לקחת עוד סדרים, כי
לא,
כשאתה מחלק באפסילון...
פתרון, אם הוא מחפש את הפתרון מהמתבדר, אתה לא פותר.
נכון,
אתה מוצא,
נכון.
אתה מסתכל על אותי עד סדר של דלתה.
אז זהו, זה שכאילו אני גם עשיתי את זה, כן? כי זה הרבה יותר קצר.
לא, זה מה שאתה חושב. כי אין לך מה לדבר אחר.
לא, אתה יכול להגיד, אני נגיד לוקח את X להיות עד סדר של דלתה בריבוע, ואם T זה, ואם X זה T חלקי דלתה, אתה צריך לקחת לדלתה בשלישית.
לא, זה לא הכוונה.
אז אני גם הנחתי שזאת לא הכוונה, בעיקר קיוויתי שזאת לא הכוונה. זה מה ש...
לא, שיפ.
אל תקשה לעצמך תמיד.
זהו, לא אמרתי, זה תחום הצבא, אני אמרתי, כל השאלה אם אומרים אחרת.
אשתדל להיות כמה שאפשר. Okay, everyone's ready? Okay, I'm ready. Okay, today we're talking about the VCS theory or Bradin-Cooper-Schleifer theory. Theory basically has three main parts. The first part talking about how in the lattice of positive particles, right? Two electrons will have some attraction between those two. When you ask yourself how can it be that two negatively charged particles attract to one another, is because the theory assumes that the lattice is not, it's a little bit flexible. So when there's two electrons, let's say in the middle of each box, those two positive particles will slightly attract to one another, and those two charges coming close to the electron will pull them together. Of course, we won't talk about this in the tutorial. I won't prove you this. A bit above my pay grade. Okay. The second step. So this one is step one. Second step is to solve the Hamiltonian of the system. I'm going to stop right here because this is what I'm going to talk about. And then the third step is using the two first steps, the attraction of the electron and the solution of the Hamilton, to prove that this system has no resistance and is a super factor when T is lower than T critical. So today we will mostly focus on the second part, diagonalizing the Hamiltonian, and we'll touch a little bit on part 3 without proving it. Okay. So, since we're skipping the first step, we have some sort of initial Hamiltonian that we get that describes the system. Right. First of all, free electron energy, where K is of course the K vector, sigma is the spin of the electron, plus or minus, up or down, and epsilon right here, it's the shifted energy, basically the energy of the electron minus the Fermi energy. And K minus F. Capital. All right. Now, to this free electron energy, we add some interaction term. Yep. Up. Yeah. Okay. So I have some interaction term where V is greater than 0. And before we even start the calculation, we can talk a little bit about this interaction term. We see here that we have a spin down electron going in one direction and a spin up electron going in the opposite direction, and they have some sort of exchange of kinetic momentum between the two. So we can clearly see that this problem sort of relates to a pair of particles existing that we can annihilate, and then two holes that we can fill back up. We know that this will dictate some sort of symmetry. Before I'm going to talk about the symmetry a little bit more in depth, let's try to organize this equation to be a little bit more sympathetic, like look nicer. Right. We see that the interaction term has a spin. The spin is already open in the interaction term, so let's try to do it again with the free electron term. So I'm just going to take this H0 and work on it for a little bit. So H0 equals to sum over K. K W up, down, sorry, up, plus K down, C K down. Also it means vectors. And again, in the interaction term, we see that all the downspin will have an opposite momentum to all the electron with the upspin. So I can arbitrarily put a minus for the case, because we're summing over all the possible case. So we just change the direction of the summation. So I'm just going to put it straight in, minus, the minus. And then I'm going to do one more step that's going to be a little bit arbitrary, and we'll see why it's important a bit later. I'm going to switch the order of the creation and annihilation term here. For now, it may look arbitrary, but it will save us time in a second. Over K. Variance K up plus minus K down, C minus K down, Bagel plus K
minus.
Yeah, it's a minus. Sorry, yeah, it's a. It should be a minus here because we're working with fermions, so it's an anti-commutator switch instead of a commutator. Yeah. Okay. And now, one last change I'm going to do is I'm going to define the new index called just K without the vector. K would be equal to index K in upspin, and minus K be equal to index minus K vector downspin. Just to simplify this equation. Overall, we find out that H, we reorganize H to be equal to over K. So, W K minus C minus K dagger minus V over K tag. K dagger, C minus K dagger, K tag, K plus sum over K, epsilon K. All I did for now is just reorganize it. I didn't do anything special. Now we can start to diagonalize it. Try to diagonalize it. First of all, I'm gonna, for the rest of this calculation, I'm gonna ignore this constant part again, because it's constant and I'm more interested in the dynamic. Second, before we go into the calculation itself, we see that this term will always give us some negative energy. But if we have, let's say, the ground state of the free electron state, which will be a vacuum, this term will give us no contribution in a vacuum. But since this term is a negative energy, we can use it to find some state that has less than zero energy, basically a lower energy than the vacuum state. So what I'm trying to say is that the addition of this negative energy term changes our ground state into something different that we assume will be somewhat dependent on this state. Now, last tutorial, when we talked about the ground state changing and there's a negative energy term, we sort of try to remove, if you remember, with the Hubbard, with the Hubbard transition, where we try to basically cut some of our space in order to find the new ground state. Right now, we're going to try to calculate it directly instead of doing some changes. Okay. So instead of the ground state being F0 or the Fermi C, we'll define some new ground state BCS. For now, we don't know what it is. We just know that it has some sort of symmetry that relates to this term. And again, this term, we said that it has structures of holes and pairs in it. So if we have some state that is some sort of superposition, some sort of communication between holes and pairs, we'll say something a bit sketchy, but we'll assume that BCS, BCS will not be equal to 0. This assumption will make sure that a ground state has some value in this interaction term. Okay. We have some sort of basic assumption about the state, and we have the Hamiltonian. Now what we need to do is to diagonalize the Hamiltonian in order to solve our equations. The first part is easy. It's just a free electron. We know it's already diagonalized. The second part is 4 operators in it. And if you try to diagonalize 4 operators, you'll find out that you need a four-dimensional matrix. 4-dimensional matrix, it's kind of hard to write it on the board. It's even harder to try to diagonalize it. So we need to do some trick. And the trick that we do in case of multi-operators terms is doing mean field approximation. What before we called the Hartree-Fock approximation. There's a much larger term associated to it, which is a mean field approximation. And in class, I'm pretty sure Efrat showed you that taking the mean field of this term, we can ignore the Hartree and Fock terms, right? What showed you this in class. And we're left with a dagger minus K dagger. C minus K tag. Tag. Mentally proof. Minus K dagger. C minus K tag, CK tag. Plus CK dagger, C minus K dagger, C minus K tag, CK tag, minus CK dagger, C minus K dagger, C minus K tag, CK tag. Efrat showed you this, proved this transition?
Yes. That it's the
Yes.
Okay, so
But without the last term.
without the last term?
yes, without the
Okay, so I'll show it. It's It's in the tutorial notes, but I'll show it anyway. It's the notes below in the end of the page. Okay. Okay. Let's assume we have two operators, A and B. I can say that A has some sort of mean value and some small fluctuation around it. So A will be equal A plus delta A, and B will be the same. It has some mean value plus small fluctuation around it. And now AB be equal to A B plus A delta B plus B delta A. Plus delta, yeah. Okay.
So you ignore.
Yeah, but I'll write it and then I'll ignore it. Of course, we ignore this. Okay, now we can use the two equations above to write delta A equals A minus the expectation value of A, delta B equals B minus the expectation value of B. Putting this back into this equation right here will give us A B equals A B plus A of B minus expectation value of B plus B of A minus expectation value of A. Yeah, see it? Overall, is equal to A expectation value of B plus B expectation value of A minus expectation value of A times expectation value of B. Okay. So this is just some sort of algebraic intuition to this equation right here, down here. Of course, when you do mean field theory, with mean field approximation, you should be careful because technically there should be also the Hartree and Fock terms here, but I'm not going to show it. Efrat already showed. I'm pretty sure the Fock cancels out to 0 and the Hartree become the constant, something like that. I don't remember exactly what.
She hasn't shown it explicitly. She just said she will be shifting the energy.
Yeah, if I'm not going to the Fock, it zeroes out, and the R3 can be consumed by the free electron. Okay, but we'll just ignore it and just take the BCS mean field. Okay. Now, let's call V times sum over K of minus K CK. We'll call that delta, and delta prime B V over K CK dagger C minus K dagger. And we see here, let's ignore for a second the last term, and we see here that the term in the expectation value in each of the operator terms has a different index and the operators outside. So those are two separate sums, and I can take this expectation value with the sum that's related to him and feed it into the delta definition. Overall, H equal to over K vector. Okay. CK dagger CK minus C minus K dagger minus delta dagger C minus K CK plus delta CK dagger C minus K dagger. There's also absolute value delta squared divided by V. This term is the term right here, and just for completion, I'm also gonna add the term that we got from the re-electron.
Relation is whether the K vector or just the K with both the vector and the square?
Over the K. Just the K vector.
No,
sometimes
not even the fact because you wrote it.
Yeah, in the sum, sometimes put a vector, sometimes not, but the sum over the K's themselves.
Yeah, but without the vector, it's also K's.
Yeah, so I probably should clarify. This is always a vector. Here. Also here. Okay, so where's my eraser? Before I'll go on, any question about the methods that I'm using right now, the math, anything? We're a pretty good pace, I can take time for questions. Now we can define our number spinor representation, which will be the operator vector, and we see that the symmetry gain in the system, in how I wrote everything, has the positive K on the left with the dagger, and the negative K on the left without the dagger, in all of these cases. And exactly the opposite when we look at positive K without the dagger, and a negative K with the dagger. So we know that on our left, so bless you. 2 K dagger C minus K, and on the right, without the dagger, well, K C minus K dagger. The Hamiltonian, okay, so, dagger, vector, conjugate. Plus the constants. I'm going to write them again. Now, we can diagonalize this matrix straightforward, or we can employ one of the many known useful transformation, which will be, for us, the Bogoliubov transformation. U above. Right. Wheeler transformation goes as follows. Okay. I'm gonna write it and then we'll talk about it a little bit. Okay. K minus VK dagger. Gamma minus K dagger equal to VK conjugate VK plus UK C minus K. We a little spoiler alert. We can always pick UK and VK to be real. So from here on, I'm not gonna write the conjugate on the V and U. I'm gonna assume they're real. Now, this transformation, as we go on, we'll see more where we picked it. But for now, a very short, very simple intuition that I found helpful is that the new terms has some sort of superposition of an annihilation and creation for a hole, we create an electron, and an electron that we can remove, put both together, which we said is how the state the ground state of the Newtonian should be, some sort of superpositions of holes and full electrons. Okay. So taking this transformation into matrix form, get gamma K minus K dagger equals UK VK K of K minus K dagger. Oh, shortly rho gamma UK. So now walking in reverse, we sort of found our answer first, and we want to find some properties of the U, K, and VK, and eventually find what they are. So first of all, because it's a transformation, it needs to be unitary. So that UK is equal to K squared plus VK squared equals to 1. UK equals cos theta K or sine theta K. We're going to resolve this in a second. VK also equal to cos sine theta K or cosine. Okay. To resolve this conflict, we simply need to see which one of those V and U are antisymmetrical in the cases. Right? So we know if we take the first equation, conjugate it, and put a minus sign on the K, we expect to see the second equation right here. So let's do exactly that. So you have gamma minus k dagger equals u minus k, c minus k dagger, minus v minus k, c k. We know this one, so we know that equating it to the second equation, u minus k equals to uk, and v minus k is equal to minus vk. So uk is the cosine term and vk is the sine term. Last thing that we need to do is to prove that this transformation really preserves the quantum properties of our operator, specifically the anti-commutation relation. We need to prove that gamma k, gamma theta dagger is equal to delta k theta. Right. If we put back in the terms you find here on the left, we get anti-commutator of uk k minus vk c minus k dagger, v minus k minus k tag, plus u minus k tag, c k tag. Equals to. Okay, I can open this commutation relation, and of course I'm going to ignore the term, the commutating term between annihilation and annihilation term and creation operator. We'll get uk u minus k tag.
Why can you ignore this term?
Because we know that to open this this term will give us 4 commutation. This one commutation relation will give us 4. We'll separate them based on the addition, and the commutation relation between ck and c minus k tag will be by definition 0. Because
this depends on the state you are working.
No, because those are 2 annihilation operators. And the anti-commutation relation between 2 annihilation operators will always be 0.
No, it should depend on the state you are working on.
Right?
Yeah, but that's not what you have. You have.
Wait. Okay. Let me.
You have only one term.
What?
You don't.
Oh no, I suppose there are 4 terms. ck commutating with c minus k tag, ck commutating with ck tag dagger, c minus k dagger commutating with c minus k tag, and c minus k dagger commutating with ck tag dagger.
Oh, okay.
I am going to ignore the dagger and the dagger, the annihilation with the annihilation. So first 2 terms is the annihilation with creation here. uk u minus k tag. ck c k tag dagger minus vk v minus k tag of v minus k tag c dagger c minus k. No, this is now u minus k tag equal to uk tag, v minus k tag equal to v k tag. we have UK tag plus BK tag. Right here, so equal to delta K tag. So it's this one, delta K tag. Okay. No, this minus is also only a commutation relation. Now, if K has to be equal to K tag for it to not to be equal 0, we can assume that in this bracket K is also equal to K tag. So we have UK squared plus VK squared, which is over here.
Yeah. Here is this minus. Oh.
So it is equal to delta K tag. We preserve commutation relation. Very good. The last thing that we need to do is to get the inverse transformation. It's very useful. We should do it. Inverse. You can either take Q and find UK minus 1, possible. But I think it's much simpler to use the fact that UK squared plus VK squared equals 1 to do this neat trick. UK gamma K plus VK gamma minus K dagger equals UK squared K minus UK VK C minus K dagger plus VK squared CK plus UK VK C minus K dagger equals K. Similarly, C minus K dagger will be equal to minus VK K UK gamma minus K dagger. So, final transformation, we explore it a little bit, so it's time to use it, put it into our equation. Just gonna write it a little long. Okay. Now I left those spaces blank for purpose. We know that since U is unitary, U dagger K equal to I, the identity matrix. So we can just put in these blank spaces that are left. UK dagger K, K dagger UK. Now this right here will be capital gamma K dagger by definition. This right here, capital K gamma And so right here will be HK diagonalized by definition. Plus K D equal to K 0, 0. Now, we know that we have two terms we need to find. EK are energies, eigenenergies, and theta K. What's the term that define our transformation? So we have two terms, and we have here two solutions, 0 and eigenenergy EK. We can use those two solutions to find theta and the energy. Let's try to reach this diagonalized state directly. Directly implying a transformation. Equals sin theta K minus sin theta K. Okay. Technically, this one is supposed to have a conjugate on it, but again, we can without breaking generality, we can take the delta here to be real. And again, cosine theta K, sin theta K minus sin theta K cosine. Okay. I'm going to spare you the arithmetics here, doing all the steps. I know I'm so nice. And the result will be okay cosine 2 theta K plus delta sine 2 theta K minus delta cosine 2 theta K okay and sine 2 theta K yeah. For this, we can get a two equations for two variables. 2K equals okay sin theta K 2 delta sine 2 theta K 0 equals minus delta cosinus K plus sin K Fine. Yep. Now, taking the square of those two equations, combining them together, give us this one, this one, 2. 1 squared plus 2 squared will give us ek squared equals to k squared plus delta squared. Similarly, if we put this result back, we can get that uk equal cosine delta k equals square root of 1 over 2, 1 plus k divided by k. Vk equals sine theta k equals square root of 2, 1 minus k ek time sine of k. Okay. Now let's start with looking at the energy for a second. We can graph it, map it, create a graph where the x-axis is a normalized electron energy, and the y-axis is the normalized system energy. Get something that looks like this. In the middle, right here, do some energy gap of delta. This will show us that if we have, let's say, this superconductor sitting in some temperature, if this temperature is small enough, so k Vt will be smaller than this gap energy, we will stay in a stable ground state solution, which will be a stable superconductor. Of course, I'm not showing that this is a superconductor. The point is more of we have some sort of gap between the zero energy that will give us some special and stable behavior under a certain temperature. Okay. We can also look at U and K graphs. Okay. Again, the graph is x-axis, the free electron energy normalized to the interaction energy, the interaction delta, and we have where k squared is dk. We'll return to this graph after we talk about the ground state of the system. This will often make a bit more sense after we talk about it. So, the last step to fully understand the system is to understand the vacuum state or the ground state, to define the BCS vacuum state. So, we aren't going to calculate directly the vacuum state. I'm going to give it to you, and then we're going to go over it, and you'll see some more properties, even some more properties in your homework. So, if we want to write the BCS ground state on the electron basis, the electron informal basis of the multiplication of the pi k of UK plus VK k dagger C minus K dagger, where 0 is the real vacuum. So, like I said before, from the beginning, our entire system has some sort of symmetries of holes and electrons. And this ground state perfectly examples that. We have some probability UK squared to have no electron in a certain state K, and we have some probability VK squared to have a pair. So we can define our state as some sort of superposition between holes and pairs. Okay. Now I gave it to you, but let's look at some basic properties that this BCS state should have for it to be a legal state. Well, first of all, it should be normalized. It should abide normalizations. So BCS should be equal to 1. Okay. Now I can define, instead of trying to multiply this big annoying thing, I can define BCS K equal to UK plus DK CK dagger C minus K dagger 0. And you'll notice that the BCS vacuum state is equal to multiplication over K of BCS K state. Okay? So what's written down here below, so the normalization multiplication here is just BCS infinity to BCS 1 to BCS infinity. So all we need to do is actually prove that BCS K multiplied by itself is equal to 1. That's all we have to do. Let's do it. Okay, so BCS K by BCS K equal to 0 UK plus VK minus k, ck, uk plus pk, k dagger, c minus k dagger. Note that the conjugate, making the conjugate of the state, will remove daggers and switch the operator, as we know. Okay. Now we have 0 uk squared plus uk pk of c minus k ck plus ck dagger c minus k dagger plus vk squared c minus k ck dagger c minus k dagger. Okay. The term in the middle, 0 out, and we only have 2 annihilation operator or 2 creation operator operating on the vacuum, or an expectation value on the vacuum. Okay. uk squared will just be uk squared, and this big term, we'll see that each creation operator on the right will have a corresponding annihilation operator on the left. So this entire 4 operator term will just have an expectation value of 1. You can use weak theory if you want. Equal to u k squared plus vk squared equal to 1.
Can you say again why the middle part vanishes?
Yeah. Well, there's 2 ways you can look at it. Let's for example look at the annihilation term, the 2 annihilation terms. You can operate on the right and it's 0.
Right.
The creation operator, you can operate them on the left. Operating in a creation operator
and
on the left vacuum will be 0. Yeah. Technically, it's operating them. Okay. Now, another interesting question is, how many electrons I have in the system? I give you some sort of, I give you a perfect equation for Vk, give you all the terms, whatever, how many electrons, physical electrons I have in this BCS ground state. Well, the simple answer is to just check it. So, BCS, dagger k ck, BCS. It's just a number operator writing on the BCS ground state. Now I can do 2 things here. I can take the BCS ground state and open it using our electron representation, but you get a very cumbersome equation with a lot of multiplication that's not really trivial, blah, 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 a lot of noise, But I think the simplest solution is to take our, I erased it, the reverse transformation and transform CK into gammas. Then operate, then put it back in. What did you? So, get BCS. Okay. Gamma KW. Okay. Gamma minus K. UK. Gamma K. VK. Gamma minus KW. CS. Just to reiterate, when we take expectation value, we try to calculate expectation value, the most important thing that you should look out for is working in a consistent basis. If your states are in basis 1, your operator should be in basis 1. If your operator are in basis 2, your states should be in base 2. Should not try to do this in different bases. It would just be a big mess. So in this case, I decided to move the operators instead of the state. Now, very quickly, we can see that a gamma k here operating on the right gives us 0. So I can remove this. And gamma k dagger on the left operating on the left will give us 0. Because again, the BCS is the vacuum state for the gamma operators. So every condition that we know about the operators of the electrons on the actual vacuum state will work when we talk about gamma operating on the BCS vacuum state. Overall, we have a little value Vk squared times gamma minus k dagger
Okay.
Now we can see Vk will represent the number of electrons we have, and Uk will represent the number of holes, which sort of aligns with what we see in this graph, where we graphed Vk and Uk, where if we have a high k vector, while there is a structure of holes and pairs, we'll still have some sort of symmetry that prefers the electron to be close to the Fermi level, which Fermi level is in 0. Above Fermi level, we expect lower occupation of electrons than lower than Fermi level. So the change didn't just spread the electron over the entire K space, only caring about holes and pairs. It's some sort of a combination between the Fermi state that we know in the free electron state and some movement that was caused during the interaction term. And again, we can see it because above the Fermi level, the number of electrons in each state quickly drop down to 0. The number of holes go up. And that's it for the tutorial.
Thank you.
Thank you.
No, thank you.
Thank you.
No.
Thank you.
Thank you.
כבר 10 דקות, אתה? באמת אתה 20 דקות.
אין מסיים מוקדם.
כן.
אין מסיים מוקדם. טוב, אני אשאר פה 5 דקות.